University. I'm a assistant professor there. Today I'm going to talk about the modeling of gas-solid flows with turbocharging. This project I started working on when I was at Princeton University in the Professor Sundaresan group. And we have been working on this project more than 1 year. And also at the same time, I'm collaborating with Dr. Kole Hemanen. He's also associate research scholar at Princeton University. So, what is turbocharging? Just briefly, the particles, when they contact, or the matters they contact, they tend to pick up some charges. And turbocharging is observed in every circumstances. For example, when you wrap your balloon, it's with your wool sweater, they tend to pick up charges and they start to stick each other. And also, turbocharging is also naturally observed in dust devils and sandstorms. This is the view from Mars. And it's a big problem for the Martian vehicles because due to electrostatic charges, all the solar cells covered with the dust. And this is the image I found yesterday night. This is because the Colima volcano in Mexico. And we can see there are lightnings here in the clouds of the eruption. So there are also some significant industrial implication of the turbocharging. Here, for example, it's a dust explosion, and turbocharging creates some hazards and inefficiencies, some power technology applications from silo flows to polymerization reactors. So the connection between the macroscopic behavior of gas-solid systems and turbocharging is poorly understood now due to the complex behavior of this flow and the lack of understanding of the turbocharging. So we start working on with kind of really simple flow configuration. This is just filled as bed. It is kind of small. It's with a square section, and the size is 1 centimeter, 1 centimeter. And here our particle is polyethylene with a diameter of 250 micron. And the bed walls are glass, and in terms of charging, it's an insulated wall. And we use nitrogen as a fluidization gas, and the fluidization velocity is 0.54 meters per second. All these experiments were conducted at Tampere University of Technology, Finland. So here I am showing two videos of our experimental study. What are the differences between this one? The first one, the left one, we conducted experiment at low humidity level. The right one is high humidity level. So what we see from these videos, when we look at the case with low humidity level, there is no slagging, and there are only few particles at the freeboard. And when we look at flow behavior at high humidity level, we can see particles are more highly agitated. So then our approach, then we said that the turbocharging characteristics of the system can be attributed to humidity level. So then we would like to model this flow configuration. So we start with the Euler-Lagrange approach. In the Euler-Lagrange approach, we solve continuum average equation of motion for the fluid phase, and we track the particles in Lagrangian fashion. And for this case, we couple them with the interface momentum transfer. And for particles, we use soft sphere model for collisions, and which in this case we use nonlinear spring dashpot model for particle-particle and particle-wall collisions. So, and these particles also, they carry charge. So then we have a turbocharging model which accounts for the charge transfer during a collision. And we also have a Poisson solver to compute to electrify at contact point. I'm going to give more details how we use the turbocharging and the Poisson solver in the next slides. And we prefer this one because we prefer to use particle tracking approach because it is easy to observe the agglomerate of particle and the breakup. So this is our charge transfer modeling. So we use this model for conductive and insulated particles. So this is Q dot ij. It's the charge transfer rate during a collision. And this equation shows our charge transfer. Here, Aij, it is the overlapping distance during the collision. We use here Heaviside function, which it means that when the particles, during the collision, when they are approaching, we take into account charge. But when they are separating each other, we don't take into charge. So here, the other parameter, this is epsilon. It is the permittivity of the system. And the red terms here, this is the effective work function differences. It's a lump parameter, so we use our experimental data to determine it. So maybe some of us not familiar with what is work function. Actually, the work function in solid state physics, just the energy you need to get one electron from a solid. So we call it effective work function because we would like to use this modeling approach for conductive and insulated particles. So then here, delta C, it is quantum tunneling distance. It's a constant parameter. E is the electron charge. And we have also the electric field affects the charging. So we have this term here. And also we have a critical condition here. If the electric field is larger than a critical point, then there is a breakdown. It is like considered like a lightning. So to compute, we need to be careful how to compute electric field because it definitely affects how your charge transfer. So we develop particle mesh type finite volume approach to account electric field effect. So we decompose our electric field in two contributions. One is the long range, the other one is the short one. For long range interaction, we saw Poisson equation here. The phi is the electric potential. Rho q is the charge density. And how we compute the charge density, we use just particle injection method. So we just simply adapt charge the particles where they belong in a cell. So then we simply, the long range electric field then equal to just the gradient of phi. So when the particles are in the same cell, so we just use truncated pair sum approach. And finally, we have the total electric field, which is the short range given by pair sum, and long range Poisson solver. And to avoid double counting, we have a correction term. And finally, the electrostatic force acting on the particle is just given by the charge multiplied by the electric field at the particle center. So then we started with a really simple experimental study, which is granular, vibrated granular bed. So it is just simple. We have a shaker here, small cup here. We have Faraday cup. We have amplifier. So we shake the particles for a while, and then we pour the particles in a Faraday cup, and we measure the charge. So these here, the particles are the same as our fluidized bed case, and also the container is glass. And for this study, we vary the humidity levels. We have a humidity level controller environment, and also we vary the total mass in the system. Before presenting our results, I would like to just introduce some model parameters. Then it will be easier to follow our discussion, I guess. So here there is equilibrium charge. What does it mean? If there is no electric field and all the particles are isolated, they get the maximum charge, which is Q equilibrium. It is a function of work function, particle diameter, and all these the electric field parameters. And if we take into account multi-particle system, and if there is electric field, the maximum charge of the system can be Q infinity. And if only collision, no electric field, these quantities should be equal. And also we characterize our strength of the electrostatic effects. It is just a non-dimensional number, which is the ratio between the coulombic force and the gravity, which is given this equation here. So it is here our first results for our vibrated bed. The left figure shows the charge per mass versus total charge in the system versus mass at a constant humidity level. So what can we see here? The behavior is not linear. This is we find it is interesting because
Tribocharging effect.
yes. Because at the first place we thought that the turbocharging is a kind of surface mechanism. So when we introduce more particles in the system, the surface area, it's linear proportion. But what we get is nonlinear behavior. So we think that it's really interesting results. So here all experimental results, and the second figure shows the total charge in the system versus the humidity level with a constant mass. So what can we see here? As we increase the humidity level, the absolute charge decreases. And these results are consistent with the previous study in the literature. So then we run the simulation with our developed approach. And here the results, which is the ratio between the saturated charge to equilibrium charge versus total mass in the system. Here the points are referred to experimental results. The line here is the simulation results. So we are more or less happy with these results. We have really kind of good agreement with the experimental results, and also nonlinear dependency. It's well captured by numerical approach. As you can see, there are some discrepancy in the really small mass and small charge. So it is a little bit difficult to measure the charge for real small amount of particles. So we went back to our fluidization case. So as I mentioned before, we have seen different fluidization behavior. So for low and high humidity level. So we took a close look in our system with a high image camera. This is the experiment for humidity level equal to 20%. As we can see, the particles stick at the wall. And also there are multiple layer formations like plus charge, minus charge, plus charge, minus charge. So then we run this. We use our approach to run the simulation. So for the fluidization case, this is what I'm showing here: the scale pressure versus total mass in the system. So this is pressure drop. It is representative of the fluidization behavior. Here the scaling, I use the total weight of the system. This is delta P0. It means that if there is no charge, then total weight of the system equal total pressure drop. So if there is a charge, it means that the particles stick at the wall, and the wall supported some part of the weight, and then the total pressure goes to 0.9. So the disappointing part of this results, our approach, it predicts very well for kind of small amount of mass, but when we go to higher, and we get some discrepancies. So as a test case, we know the total charge in the system. Then we run the same simulation with the uniform charge distribution. There is no turbocharging. And we get really good results. So this is really surprising. Then what we get, when we look at the simulation results, we cannot predict the multi-layer formation. So then we ask the question, why our model is failing? So for the CFTDM approach, we soften the particles. We don't use the exact Young modulus. So then it leaves artificial acceleration of the charge transfer. So when we look at the mean charge, we have a good prediction. But when we look at the probability density function of the charge, there is a significant differences. So if we use harder, or the stiffer particle, and it means that the acceleration factor is lower, we getting better results. So the point is here, so the charging rate does matter. So you cannot use really softer particle for this case. So, but it is not that efficient, or it's not that computationally possible to run really stiff particle with this approach. So then we said that why don't we go with Euler modeling? Because with Euler modeling, we don't track the collision. So then it allows us to run simulation with lower acceleration factor, and also it allows us to run simulation for larger domain. So this is a hard space particle collision model. This is the collision law, or the charge evolution after the collision. So starting from the Boltzmann equation, with assumption of the mass value distribution of particle velocities and charges, And also by following Jenks and Richardson for the collision term, which means that we decompose this collision canal in two parts, collision flux and collision source term, we can derive our transport equation for mean charge. So this one is a supplementary transport equation with the standard two-fluid model. So in this one we have the time derivative, the advection term, and we have also two additional terms on the right hand side of this equation. So here the first one is related to electric field, the other one is the charge diffusivity due to collision. And there's some similarities to charge transport in ionic solutions. So here the sigma q is the turboelectric conductivity and the kappa q is the turboelectric diffusivity. When we look at the turboelectric conductivity, it is function of radial disturbance function, particle diameter, Poisson ratio, and granular temperature. So similarly, for turboelectric diffusivity, it's given by this equation, and we recently published all this derivation in our recent paper. So then we want to validate our derivation. So we develop Euler hard sphere code with turbocharging. So this is just simple test case. It is fully periodic box. We thermalize the particles here. We have B model distribution. The left part is the positive particle with the positive charge. Right part is the particle with the negative charge. So after a while, there's a charge transfer and they get to 0. So here the lines are our hard sphere model prediction. The circles are Euler approach. These figures for two different solid volume fraction. So when we look at the results, we say that we have good agreement with our Euler Lagrange hard sphere code. So to run the fluidization case, we develop boundary condition for charge. So this one for here we equating the flux at the wall and the interior, and finally by using the kinetic theory approach, which then we get a Robin boundary condition for charge. Here the differences is we have sigma WQ, which is the turboelectric conductivity at the wall. So we implement this charge transport equation in open form, and we run with the two-fluid model, standard one. So here I'm showing the fluidization case for high humidity level, with low humidity level, and with Euler code. So when we look at this one, we have some similarities between experiment and our numerical simulation, but unfortunately we couldn't predict the bed height very well, and also there are some differences between the mean charge predictions. So if I summarize what we have done, we developed reliable and robust CATM approach for gas solid flows with turbocharging, and then charge transfer is the function of effective work function difference and electric field. For electric field, we develop finite volume PPM approach. We perform numerical and experimental studies of vibrated bed, and we tune our work function difference by experiment results, and we compare our numerical simulations for vibrated bed, and we say that we have good agreement. For fluidized bed case, our predictions, it is not good as vibrated bed, and we develop two-fluid model, and we are still working on it. So for current and future research, so for this part, the electric materials, up to now we assume that the charge is located at the center of the particle, but this is not the it's not the case for the electric material, because there will be kind of surface distribution. What does it mean actually? So if you take into account the polarization, the particles of the same charge, even they can attract each other. Okay, so what we done, we perform simulation campaign consists of 300 simulation. In this simulation, we have periodic channel, and we vary the electrostatic force and all the polarization. So the main point here, what we see, so if this is the case, it's a dry case without charging. This is the only electrostatic force. So what can we see? That there is a kind of meandering flow in this stuff, because the particles, they would like to minimize the electrostatic energy. So if you look at the high polarization case, the meandering flow behavior is just disappeared, and the particles they form sheet and they just fall down. So then the main message from this, so you cannot simply lump the polarization and the electrostatic effect together. So this is, and also we have been working on the size-dependent charging. This is a kind of long debate. There are several studies. They say that the small particles they pick up a minus charge, big particles they pick up positive charge. For example, this is our fluidization case. It is really just a small one. Then we have a kind of charge distribution based on the particle size. So this is end of my presentation. If you have a question, I'm happy to respond.